was invented, when it was started, and different type of ionization technique. So in mass spectrometry, there are some core component. One is ion source. So we have ion source, and then we have mass analyzer and detection system, and then data processing. So here, as you can see, there's a typical mass spectrum for folded protein. So as I mentioned, that folded protein will have less charge state, only few charge state, and protein will be unfolded, so you see more charge state. Okay. Um, okay. So let's start. So the main function of mass spectrometry is weighing molecules. Okay. So let's say a pharmaceutical company, they actually synthesize, or they actually make production of aspirin. Okay, so this is aspirin, and the molar mass of aspirin is 180 gram per mole. So the gram per mole, we call it Dalton. Okay, Dalton, named after John Dalton, the scientist who actually get the modern atomic theory. And then we have like big molecules like hemoglobin. Hemoglobin has actually four subunits. So alpha alpha prime, beta beta prime. So four subunit. Each subunit is kind of 16,000 gram per mole or Dalton. So you have four. So altogether you have kind of 65,000 gram per mole or Dalton. So so as I mentioned, that main function of mass spectrometer is weighing molecule, weighing single molecule. Okay. So there is a difference between analytical balance and mass spectrometry. So mass spectrometry measures the mass of single molecule. Okay. Uh, and but the traditional analytical balance, they actually measure the mass of molecules in bulk. So what is the difference between analytical balance and mass spectrometry? Like the word balance or analytical balance that we mostly use in our lab, that can measure from kilogram to milligram. Then we have precision microbalance and quartz balance. They can measure microgram and nanogram. Okay, so we have a mass spectrum, analytical balance or precision microbalance in our lab that can actually measure up to not milligram, microgram. Okay, but the mass spec actually measure the mass of single molecules, um, and it's actually measured the mass of things that are kind of gyptogram, autogram, or yatogram. Okay, so then these are very, very small things, as you can see, 10 to the power minus 21, very tiny things. Okay, so that's why we need a new type of unit. So we use as a Dalton. Dalton is gram per mole. So traditional mass spectrometer that can measure from Dalton to kilodalton, and then we have native mass spectrometer or multi matrix assisted laser desorption time of flight mass spectrometry that can measure up to couple of megadalton. And then we have CTMS, okay, so charge detection mass spectrometry that can actually measure megadalton to gigadalton. And then we have NEMS, nano electromechanical resonator, that can measure the mass up to gigadalton. Okay, so these are the high mass measurement instrument, and this is low mass measure instrument of the single molecules. Okay, so in analytical balance, we measure the mass of bulk, like 5 gram of aspirin means you need to use Avogadro number. You need to convert that gram into mole, and then you can uh, um, use Avogadro number, and you can tell that how many molecules present in 5 gram of aspirin. So you measure the mass of maybe 10 10,000, like it's 10 to the power 23, as you know, the Avogadro number. So it is actually, we're measuring the mass of molecules in bar, uh, um, using analytical balance, uh, ba- uh, um, but for mass spin you are measuring single molecules mass. Okay, so there would be some question, what is the relationship between Dalton and gram per mole? What is the mass range of analytical balance? What is the mass range of traditional mass spectrometer? And then mass range for native and multi-top mass spectrometer. Okay, so mass spectrometer has three main components. Okay, the ion source, mass analyzer, and detector. Okay, so ion source, what is the function of ion source? So the function of ion source is to generate gaseous ions. Why we need to transfer sample into gas phase? Because in gas phase all the molecules are separated from each other. Okay, so then you can measure the mass of single molecules. But when molecules they are present in liquid form or solid form, they have very strong van der Waals force or intermolecular force. Then you cannot separate them. So you cannot measure the mass of single molecules when they are in liquid phase or solid phase. You can only measure the mass of single molecules when they are in gas phase. So that's why you need to transfer your sample from liquid phase or solid phase to gas phase. So, and then you need a source that can actually generate the gaseous ion. So there are many different type of ion sources. ESI, electro spray ionization, that's mostly used ion source now. And then you have multi matrix assisted laser desorption ionization, atmospheric pressure chemical ionization, electron ionization, desorption, electrospray ionization. So there are a lot of different type of ion source you have. And then you have mass analyzer. What is the function of mass analyzer? Mass analyzer separate ions and measure their mass to charge ratio. Okay, so that's the actually this is mass analyzer. This is the main component of mass spec that's actually measured the mass. So there are many different type of mass analyzer. You have time of flight. So you gather all the gaseous ions, and then there is a long tube. You actually allow them to compete or run through the tube. You know the distance of the tube. Okay, so you know the length of the tube, and once you actually push them, and then how they run. So smaller molecules they will run faster. The heavier molecule they will be run slower. So from there, and if we know their kinetic energy, from that kinetic energy equal to half mv square. From there we can measure the mass. Okay. So you can also use orbitrap. So you have ions and you rotate them around the electrode, and then you calculate their angular velocity. So the smaller ion will have a higher angular velocity, but heavier ion will have higher angular velocity. So from that angular velocity, you can measure the mass. Then you have quadrupole and Fourier transform mass spec. These are the different type of detector, mass analyzer. And then you have detector. Detector, what is the main function of the detector? Detector measure the abundance of ions present in the sample. Okay, so you prepared a sample, maybe 5 micromolar or a couple of molar solution, and you can calculate how many molecules there in your molar solution using Avogadro number, and um, and then this detector also will be telling you how many molecules present in your sample. Okay, so we'll be generating all the gaseous ions. So mass analyzer will be separating ions based on their velocity or angular momentum or some kind of separation, and then it will actually measure their mass or mass to charge ratio, and then detector will be measuring the abundance, how many ions present in your sample. Okay, it's not that all the ions it can transfer, because it's sometimes very difficult to generate uh, ions from liquid and solid. So the ions you actually generate and transfer, and how many actually reaching the detector. It's like a marathon. Many people maybe start with the marathon, but um, in the final line, maybe only few people will be crossed. So detector will be actually measuring how many ions actually reach to the detector. So you have different type of detectors. So you have micro channel plate detector, you have electron multiplier, you have charge detector, you have NEMS, nano electro mechanical resonator, you have cryo detector, the superconducting tunnel junction. These are detector, okay, and then you have data system that will process all those information and give you the spectrum, mass spectrum. So now you need to introduce your sample to the ion source. You can use direct infusion, so you have a capillary, directly you can put in the ion source. You can use HPLC connecting with mass spec, so then this will be LCMS. You can also use MALDI as an inlet, or GC or electrophoresis can be act as an inlet. Okay, so in the mass spec, the three component ion source, mass analyzer, and detector need to be put in high vacuum system. So why high vacuum? Because we want to measure the mass in high accuracy. Okay, but if you have gas molecule inside your mass spec, that can contaminate your sample. So that's why we need to pump out all the air molecules inside the mass spec. So we need to take them out. We need to pump them out. Okay. So that's why we need high vacuum system where you do not have any molecules or anything. Only your sample will be introduced so that we can measure the mass with high accuracy and precision. Because if you have air inside your mass spec, then your mass measurement will not be accurate. Okay. So these are the questions. I will be sharing all the slide. So that's you know what you need to know from this, and then there will be also a assignment after 3 days of training. There will be 100 questions assignment that you need to submit within 1 month. Okay. So then how all those things started, okay? So it started with J.J. Thomson, the J.J. Thomson who got Nobel Prize, who actually invented and discovered electron. So J.J. Thomson was born in Manchester, and he was a kind of prodigy. So prodigy means like he finishes high school very early age. When he was 14, he finished his high school, and then he wanted to be an engineer. His parents also wanted to send him to engineering school, but his father died, passed away, and then her mother cannot afford her to send to the engineering school, because that time the tuition for the engineering school was higher. So instead of becoming engineer, his his mother actually sent him to Cambridge to study mathematics. Okay, so then he went to Cambridge and studied mathematics. But then eventually he became the professor in Henry Cavendish lab in Cambridge. Okay, Henry Cavendish. Maybe you don't know him. Henry Cavendish, who actually discovered hydrogen. Okay, and then he established a lab, Cavendish lab, where actually also DNA structure was resolved, and most of the actually renowned professor are from Cavendish Cavendish lab. Okay, so he was appointed as a Cavendish professor of physics, although he was not very good in experimental physics. Okay, but he was very good in mathematics. Okay, so he was doing the same experiment. This is a Cook's instrument that in around 1800, a lot of people did research on this. And then, like others, he was actually using different metal bar, like metal bar made out of maybe copper, zinc, and then he connected this with circuit, and he also put some magnet, and this is fluorescent coating, um, and then he is actually seeing that some particles of light are coming from the cathode, and that way that the cathode ray was discovered, and eventually he saw that this cathode ray turned into the positive side of the magnet. So that way he knows that this particle has negatively charged, and then he named it electron. Okay. Um, but that was mostly known like cathode rays. Not that he actually produced the cathode rays first. A lot of other people also observed these cathode rays. But what is unique to him is that he was a mathematician. Okay, so what he did when he found these cathode ray, he actually measured the mass of electron. Okay, and also measured the charge of the electron. Okay, because he's a mathematician, so he used all the physics law of kinetics and potential energy, and how it's actually cathode rays deviating in presence of magnetic field. From that information he was able to calculate the mass of the electron and charge of the electron. So he is the kind of first mass spectrometrist. um, what is always the interval about that, so the top is there. Okay, okay. Okay. So that's why he actually got Nobel Prize. Okay, so he measured the mass of electron and also the charge of uh, electron. Okay, so and he got actually his Nobel Prize in 1901. So and then he has a student. His name is Francis Aston, and then he asked him to modify and develop a mass spec that they can use for measure the mass of different elements. Okay, hydrogen, chlorine, bromine, iodine, neon. Okay, so so he measured the mass of electron. So he got Nobel Prize. Then he asked his students, Francis Aston, to make a mass spectrometer that can actually measure the mass of elements. Okay, so then Aston and also J.J. Thomson, so developed a new type of mass spectrometer. So they use a glass bowl where they used to put some sample there, and so that they can heat them up because it need to be vaporized. Okay, and then he put lot of electrode there, and there they put photographic plate because that time they didn't have mass analyzer. So photographic plate they used to see whatever the elements actually produce here, they will be transferring, and they may have a spot on the photographic plate. So they use photographic plate a lot that time as a mass analyzer. Okay, so that's the actually this is the second mass spectrometer, and this is the third one that was built just after First World War, around 1919. Okay, and so Francis Aston actually the first person who actually able to detect the mass of isotopes. Okay, so what's happened? So he put some neon gas there, and then um, he, instead of getting one peak, he got two peaks. Okay, and then he was very surprised that why neon is giving me two peak. One is very pronounced, but other one is not very pronounced. Okay, so it's subtle and weak. The first one. So that way he actually discovered that neon has two isotopes. One is neon 20 and neon 22. So this is neon 20 and this is 22. Um, and then he also investigated the mass of chlorine. So he got four different mass when he ran chlorine. You also see some other stuff that's actually when he ran chlorine, he saw that's there are carbon monoxide, carbon is 12 and oxygen is 16. So he saw something that carbon and oxygen join together and carbon monoxide, because carbon monoxide is also present in the air. He saw a lot of oxygen, 32, and then he saw four peaks. So 35, 36, 37, 38. So then he was surprised whether chlorine has four isotopes or what. Then he realized actually no, it has two isotopes, 35 and 37. But chlorine sometimes actually in gas phase it's react with hydrogen, and it's actually produce hydrochloric acid. 36 actually hydrochloric acid, hydrochloric acid with chlorine 35 isotope, and 38 is chlorine 37 with hydrogen. And then he also saw 44, so which is carbon dioxide. Carbon is 12. We have two oxygen, 32. So you add up, and then you see that's carbon dioxide mass. So that's how all things started. So J.J. Thomson measured the mass of electrons, and his student Francis Aston, he is kind of a real molecular mass spectrometrist who actually first measured the mass of all the elements that we see and molecules. Okay. Then that was the work, and then there was a Second World War. There was a okay. So there is another guy in USA. He is a Canadian American scientist, Arthur Dempster. After the First World War, so he also developed first mass spectrometer. Okay, so he um, because in the Francis Aston there was no ionization source. Okay, he just put his sample here and heat them up, and that way, and there was no mass analyzer. Okay, there was no ion source actually. Um, so um, so Arthur Dempster, who actually invented the first ion source, he named it electron ionization. So what he did, he took the filament bulb, like the cathode ray, coming from the bulb. Okay, so he took the a bulb, and then, as you know, that's when we lighten up the bulb, it actually generate all the cathode ray, means electrons, and then he introduced his sample there. So then in his sample, uh, his sample will be interacting with the beam of electron, and then in his samples inside there is also electron will be repelling each other, and then some of the electron will be removed from the analyte of the sample, and then it gets actually ionized. Okay, and then he generated his radical cation, because electron was pushed from the analyte, so it's created radical cation. And then he also created some electrode where, as he was generating cation, positively charged particle or analyte, then he applied negative voltage in this electrode so that ion can move. So you have positively charged analytes, and then he put negative voltage using some electrode, and then ion moves and go through the electrode and then enter into the mass analyzer, and that way he can detect all of his analytes. Okay, as he is using electron cathode ray to ionize his molecules, so that's why it's called electron ionization. But it was very, very harsh electron, because it's a very, very high energy electron. So to do this, you need to actually have the potential difference, need to have 70 electron volts. So it's very, very harsh, and sometimes it's actually fragment the whole molecule. It generates molecular ion, but it's also fragment the molecules. And then there is an energy diagram for that. Okay, so to sum up, Debster around 1918, so he actually developed the first ionization source or ion source using electrons. So he used cathode ray to generate the molecular ion. So you have your analyte, and then you have very high speed electron that's coming from your cathode ray or bulb, and then these are very, very high energy electron, as I mentioned, the 70 electron volts. For example, the UV light can give us kind of 5 or 6 electron volts. So this electron is 70 electron volts. It's very, very powerful. And then you have radical cation, and then electron will be removed, because you have also electron inside your sample, and then you shine the electron, you pass the electron through your sample, so then you have double electron, and then that electron is removed, and then you have radical cation. So this is your radical cation. You also see lot of other peak. That's actually the fragment peak. Okay, so it was good electron ionization, but the only problem is that the electron is very high energy electron, and you see molecular ion, but you also see lot of fragment ion. Okay, so then this is the mass spectrum. So in mass spectrum you have two axes. So x-axis you have mass to charge ratio, and this is a molecular ion. Molecular ion is the mass of your molecules. Okay, that's called molecular ion peak. But you also see a highest intensity peak. Okay, so this is abundance. Okay, so um, if a peak abundance is 100%, that's called base peak. So this one is a base peak. So base peak show 100% abundance, and molecular ion peak, that's actually related with your molecules. So you see y-axis, you see abundance, you can see absolute abundance or relative abundance. Relative abundance 0 to 100, absolute abundance whatever you are getting, like 10 to the power 7, 8, 9, or 15. It depends on what type of mass spectrometer you use. And then you have base peak, which has show 100% abundance. So this is a mass spectrum of ethyl benzene. So can you identify which one is molecular ion and which one is base peak in this spectrum? Yes, sir. The negative one base peak. Negative one is the base peak and molecular ion is one of the things. Great. So this is the molecular ion peak and this is the base peak. This is base peak because this is 100%. Okay. That's how we can identify. And in x-axis you have mass to charge ratio, y-axis you have abundance. It's relative abundance because whatever the real abundance, you converted then 0 to 100. Okay, let's say in class you have an exam, but your teacher maybe graded all of your exam out of 100 or out of 50 25, but you converted all those things in GPA 0 to 5 or 0 to 4 scale. Same thing, you get the abundance, you you take the absolute abundance of this one and make it 100. Okay, so divided by the same, you will get 1 and then multiply by 100, so you will get the you converted that to 100%. Okay, that's the highest abundance, and then that way you can calculate the relative abundance of all other peaks present in the mass spectrum. Okay, so after invention of electron ionization, so the problem with electron ionization is that you use 70 electron volt of energy, which is very high energy of electron, and then you see molecular ion peak, but very small. You mostly see fragments. So your molecules actually break down into small pieces. So then we need to actually we need to create something soft ionization technique. Can we make something very soft ionization technique, because electron ionization technique seems like very hard technique. So then these two men, Munson and Fulk, they were working in Texas while failed. Okay, so in Texas, as you know, that South Gulf of USA, so Gulf of Mexico actually. So they, most of the oil refinery are there. So they were working on oil refinery, but they were using electron ionization technique. But they are having, whenever they actually try to ionize their petroleum product, they saw a lot of fragment. Then they try to improve the ionization system. Okay, so you have your analyte and then you have electron. Your electron is very powerful. When electron meet with your analyte, it breaks down the analytes. Okay, it's like a fighting between
না
two people.
ক্লাস
Okay,
চলতেছে তো ক্লাস
and
করে
then
যাবো
you
আর কি
might need a mediator. Okay, so you need a mediator.
এই
um,
2টা বাজবো
so they thought that, okay, if they introduce some kind of gas
কেমিস্ট্রির উপরে
and
ক্লাস আর কি
ionize those gas by electron, then gas actually ionize the
কেমিস্ট্রির
analytes.
উপরে
Okay,
একটা
that
ক্লাস
way you can soft it, you can make it soft. Okay, so try to introduce, so still you have electron beam,
এই তুই
but
আসছে কালকে
they
আসছে
actually
কালকে আসছে
introduce some reagent gas inside the ionization zone. So then the electron interact with the
না না
gas,
কিন্তু
reagent gas,
করতেন তো
and
কিছু
then
মানে করতেছি
reagent
আপাতত করতেছি
gas first ionize, and then it's ionize your analytes. Okay,
না
so
সমস্যা ওটা সমস্যা
that's called chemical ionization. Okay, it's sometimes what's happened whenever I have fight with my wife, so we have fight. Okay, so then we do not, for a couple of days we do not talk each other. We communicate through our kids. Okay, I'll be telling my daughter, okay, can you tell your mother these and these things, or maybe I will be telling my son, can you tell these and these things to your mother, and then my wife will also be communicating through mediator. Okay, so there's mediator, kind of, because we are having some disagreements and fight, so then we do not talk directly, then in between we have some middleman. Okay, so same thing, electron, previous electron ionization technique, you have electron and then you have analytes. So when they directly interact, they have fight. Okay, then analyte breakdown, then these two men, they introduce some kind of reagent gas, so that first they interact the reagent gas with electron beam, and then that gas actually ionize the analyte. That's why it's called chemical ionization. So for reagent gas, they started using methane, ammonia, and isobutane. Okay, so and this technique is still actually used in GCMS. Okay, so what's happened if you have methane? Methane is a reagent gas, and then you have electron, that cathode ray. It will interacting with methane, and it will excite the methane, and then it will produce some radical cation, and then once you have this cation, that can actually interact with your analyte, and then you can have a protonated analyte. Okay, so this proton means hydrogen will be attached with your analyte. Okay, so in chemical ionization, you do not see radical cation in the mass spec. In chemical ionization, you see protonated analyte, means one hydrogen will be attached. But then a new problem started, because these gas started reacting more and more with electron, and they create more and more cation. All of those cation actually also interact with your analyte. Then you have lot of adducts. Adducts means you have analyte, but something attached with that analyte, that's called adduct. Okay, so the lot of adducts. So they created a software technique, less fragmentation, but then the new problem arise, started, that your analyte also making some adduct formation with other cation. Okay, so now you have same compound but two mass spectrum. Okay, same compound. So you have pentobarbital, barbital. It's actually nominal mass, or molar mass is 226, and then you have spectrum A and spectrum B. Now you need to tell me which spectrum will represent chemical ionization. 227. Sorry? B? Why? Why B is chemical ionization? Can you justify?
রাত 10টা বাজে
There is a hydrogen attached with the 226 molecular weight. That's why we got NH plus, which is 227. Okay, great. Any other indication? Formation is 255. Okay, adduct formation is 255. Yeah, that's another indication. And also, do you see more fragment here? Is it right? Do you see these fragment are here? No. In chemical ionization, you see less fragment. You see some fragment, but less. But here you see more fragment. These are all fragment. These are not. So molecular ion peak is very very small in electron ionization. So you see that this is electron ionization, because you see lot of fragment and tiny bit of molecular ion
আমরা
peak.
বাড়াটি
But
করাই
for
দেন নাকি?
chemical ionization, you see the adduct like hydrogen are attested with the analyte, and you also see adduct formation and less fragment. Okay, so now you know that if you see spectrum, that way you can identify which one is electron ionization, which one is chemical ionization. But the chemical ionization having a problem that you still seeing some adduct. Okay, fragmentation is less, but you are seeing some adduct. Then how you can remove this adduct? Have any idea how we can chromatography? Okay, chromatography will separate your molecules, but that's because we are talking about ion source. How you can improve your ion source, how you can make your ion source even softer, that you will only see one peak and nothing else. No fragment, no adduct. Can you make it? Multi process? Sorry? Matrix formation process. Multi process is yes, multi. Okay, so yeah, multi means you can use laser. Okay, another way. But the multi problem, when you use laser, you actually generate a lot of small ions because you are using laser. So that's actually yeah. So here in the chemical ionization, we are using methane, ammonia, isobutane as a gas. Can we use other reagent that will not form any adduct? Inert gas? Yes. Argon? Argon or cheapest argon is expensive. Do you know any very cheap inert gas? Not helium. Yes, correct. That means now you are thinking as an analytical chemist. Okay. Now you can make a new method. Okay. So then what you thought? Exactly, they thought that okay, instead of using methane or isobutane or ammonia, whether why not we use nitrogen? Okay. So then another technique was created that's called atmospheric pressure chemical ionization. Atmospheric pressure because you use nitrogen, nitrogen can stay in the atmosphere, so that's why it's called atmospheric pressure chemical ionization. But they encountered with another problem because nitrogen is inert. So ionizing nitrogen with electron is difficult because nitrogen inside nitrogen you have triple bond. Is that right? One sigma and two pi bonds. So it's nitrogen is very difficult to ionize. Okay. Then to ionize nitrogen, they use another electrode. Okay. They use another needle inside the mass spec. So that's called corona discharge needles. Okay. So you have um, um, so then they introduce nitrogen gas instead of methane, ammonia, or isobutane. They introduce nitrogen, but they also find that they are not detecting any molecules because nitrogen cannot ionize other molecules because nitrogen is so inert that it's very difficult to ionize the nitrogen. So then they introduce another electrode, secondary electrode that can actually ionize the nitrogen. But then there was a corona discharge, so to cool it down they also introduced little bit of water, okay, to cool it down. So in atmospheric pressure ionization they use nitrogen and they also use little bit of water to cool it down, okay, and they need to use a secondary needle or electrode, okay. So then you have nitrogen. Nitrogen will be still they have cathode ray. Nitrogen will be interacting with high energy electron, and then it will be forming some cation. Then nitrogen will be also reacting with water vapor, and it will also make some complex. And then you have analytes. Analyte will be actually joining with water vapor. So then you will have water based adduct. Okay, so you will not have any other adduct but in atmospheric pressure chemical ionization, you will see water added because you use water. So this is actually APCI, atmospheric pressure chemical ionization. This is used in pharmaceutical company, and it can actually use to identify metabolites or molecules around 1500 Dalton. Okay, so this is widely used now, but you see water adduct because you use some water and nitrogen, so that's why you also see some water adduct. Okay, so now can we make a ionization source that where we will not see any water adduct? Is it possible?
You did, sir, the photodissociation.
Sorry.
You using UV and IR photodissociation.
Oh no, that's for fragmentation. Okay, so they use water solvent. Can we use any other type of volatile solvent?
Alcohol.
Yeah, alcohol means methanol or ethanol. Great. Yeah, that's what another guy did. Okay, so I'm just showing the atmospheric pressure chemical ionization spectrum that they published around 73. You see, Dumpster or J.J. Thomson, they started everything around 1890. Then he got Nobel Prize in 1901, and then around 1918 and 19, Francis Aston, they built their first, second, and third generation of mass spec, and then Dumpster in USA he built, and then it took kind of, you see, kind of 50 years to develop another technique like atmospheric pressure chemical ionization. So they use chromophore solvent, and that way they actually measure the mass of cocaine and methadone. Okay, so this is the testosterone, like the hormone. So they use this technique. Okay, as I mentioned that they use water. Instead of using water, if we just use organic solvent, okay, because we know that organic solvent, they are kind of volatile, they evaporate quickly, they will not have any adduct. Okay, and then if we do not use any electron, but we use some electrolysis to generate ions. Okay, so then Malcolm Dole and John Fenn, they were actually working in Yale University. So Dole actually first created the electrospray ionization, and then Fenn continued work on Dole, and actually what he did in 1984, John Fenn actually he published his first paper on electrospray ion source, and later he got the Nobel Prize. Okay, so what he did, so he dissolved it, analyzed in water and organic solvent. Okay, so mostly he dissolved it, analyzed in organic solvent, and then he has a stainless steel capillary. So in stainless steel capillary, he applied the voltage on the capillary. There is no electron here. He didn't use any electron because he knew that using electron will maybe make some fragmentation or anything. So he has a stainless steel capillary, and then he dissolved his analyte and sample in organic solvent. He passed through this analyte solution through the capillary, and then he put this in the circuit. So then he actually take out all the electron from the analytes, then analytes become positively charged. And this capillary, stainless steel capillary, is so tiny diameter that when you actually push them, pressurize them, so it creates a Taylor cone. And then in the mass spec electrode, you need to introduce negatively charged, so that if you are generating positive ion droplet, then you need to apply negative charge or negative voltage here so that they can move and they can enter to the mass spec. So this is how he built his electrospray ionization. So in electrospray ionization, so he used organic solvent. He didn't use any electron or cathode ray, uh, no other chemicals. He just used organic solvent so that, and he also heated that capillary so that organic solvent will evaporate quickly and it will so organic solvent they have wings, okay, they will mix with the analytes, they will evaporate and they will turn the analyte into ions, okay, but they will not be attaching with analytes. And then if you run this sample using mass spec ESI technique, you will only see one peak, only one big peak, okay. So you see, like this is a compound synthesized by my colleague in his lab, and the mass of this compound is 326. We need to add. So in ESI, it will be only hydrogen will be attached with the analyte. So one hydrogen is attached. So the theoretical mass after adding hydrogen is 327, and you only see 327. You see some tiny bit of it. It may have some sodium adduct, okay, but its abundance is less than 10%, very tiny. You just see one beautiful peaks, okay, because of his contribution of making this new method. So he got Nobel Prize in chemistry. So if you have pesticides, so propanil is a widely used herbicide in USA, and so you can see that this is the theoretical mass is 218, and then if you run these pesticides inside the mass spec, so this is with LTQ machine. So then you can see that its mass is 218, and then you may lose some of the hydrogen. Two hydrogen are lost, so that you also see something at 216. And then you can actually select these ions. Okay, in the mass spec, you also have a ion trap. Okay, so ion trap. We will be talking more about ion trap. So you can trap that ion, and then you can apply some voltage. You can apply some voltage and try to break down the molecule. So if you apply 10 voltage, 30 volt, and 50 and 100, when we applied 100 voltage, we saw there are some other peaks actually emerge in the mass spec. Okay, when we apply this voltage, we saw that there is another peak is 133. So this is the mass of your intact pesticides, propanil. And then if you take the mass difference between 218 to 183, it's actually 35. So it means you have two chlorine there. So it means these bonds are broken, and that's why you see this peak. So also this bond can be broken. That way you can identify there's okay 157. So if you see some 59. So if you see something, so this the whole thing is 218, and then if this part is broken, the leftover mass is 160 or 159. So that's why you also see a peak. So that's this is the place where this carbon nitrogen bond can be break. And then if you have this leftover, it means it's a metabolites. Okay, so if you introduce these herbicides um, in the agriculture field, and then it can, if it see the UV lights or it introduced by soil microbe, then it can also produce some of the metabolites. Maybe the chlorine will be degraded, so chlorine will be degraded fast, and then this carbon nitrogen bond will break and they will create smaller molecules from the propanil. Same thing, glyphosate. This is a pesticides. Okay, this is also another herbicides actually. And if you do um, uh, so this one is ESI, no fragmentation, but this one is fragmentation. When we do the fragmentation, we can see that's where it breaks. So we can see that this phosphate can break from this glycophosphate because the phosphate mass is 87. So that way we can identify where it can actually break using ESI as well as tandem or MS spectrum. Okay. So the ESI has lot of benefit. So another thing is that ESI can ionize protein. So protein is not like small molecules. Okay, in small molecules you have only few atoms, but in protein you have kind of hundreds amino acid. Each amino acid you have kind of 20 atoms. Okay, so this is cytochrome C. This is a protein that present in our respiratory system. Um, um, so it molar mass is 12, around 12,000 gram per mole or Dalton. And then if you prepare this protein sample in mass spec and if you run the ESI, and you will get you will not see one peak, you will see lot of peak. So you will see different charge state. Okay, so inside the protein you have a lot of basic amino acid. You guys know what are the basic amino acid out of 20 amino acids? Some are basic amino acids.
Yes, positively charged amino acids.
Yes, yes. Can you tell me the name of couple of basic amino
Histidine, histidine, arginine,
acids? Okay, there are three basic amino acids.
lysine also.
Lysine, yes. Lysine, arginine, and histidine. There are three basic amino acids. So these basic amino acids, they have nitrogen. Is that right? In their side chain, in lysine, you have CH2, 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 and then you have NH2. Is this right? And then you have amino group. That nitrogen can take a proton. So it means it can act as a base because it can receive the proton. Same thing for arginine. You have guanidium ion, okay, and then that can be also protonated. And histidine, you have imidazole. So in imidazole, you have a nitrogen. That nitrogen can be protonated, okay. So inside cytochrome C, you have lot of basic amino acids, okay. That all basic amino acids they can get protonated. So if 7 of the basic amino acids are protonated, you can see the peak here. It seems like the 13 basic amino acids are protonated. So you see this is the base peak, but at least like 16 actually basic amino acids are there. That's why you see from 7 to 16 charge state for this protein. Okay, so you do not see one peak, you see multiple peak. We will learn how to calculate the charge and mass from the uh, um, mass spectrum. Okay, maybe today or tomorrow. Okay, type permits today, or if not, then tomorrow. Okay. So then how ions are actually formed in electrospray ionization? There are three mechanisms. One is called ion evaporation mechanism, another is called charge residue mechanism, another is called chain ejection mechanism. Okay. So as I mentioned that you have analytes, if you have small molecules analytes like pesticides, so this is a small, and then you have water droplet because you use organic solvent and water. So then you have a droplet. Okay. So ion evaporation means ion will be evaporated from the organic solvent. Okay. If you have a small pesticides or small metabolites and molecules, that ion will be evaporated. Okay. So you see that ions will come to the edges of the droplet and eventually it will be evaporated from the big droplet. Okay, that's how small molecules ions are formed. But if we have a protein, so protein cannot be evaporated because protein has so many amino acids, so many atoms, so many things inside the protein. So they will be following charge residue mechanism. Charge residue means all solvent will be evaporated, but then only protein will left as a residue. Okay, so So that's, and they will be charged. There will be multiple charge. Okay, that's called charge residue mechanism. And this is for globular protein. If protein is folded, but if protein and polymer they are unfolded, they will follow charge ejection model. Okay, so that means they will be ejected from the droplet and they will have a charge. So this is for disordered protein and unfolded protein. So this is how electrospray ionization um, form different type of ions. Okay? Then we have different type of source. We have different type of. This is electrospray ionization source. Sometimes we also, if you use a heater, okay, thermocouple to heat up the source, then it's called heated electrospray ionization source. And then you also have atmospheric pressure chemical ionization source. So so you have different type of ionization source. So you have electrospray ionization source, you have atmospheric pressure chemical ionization source, and then you have AC source, means heated electrospray, means if you also use some heat to desolvate or evaporate ions. Okay, and these are the different. Some of the things may be in France, because this is actually from where when I was doing my PhD. That slide I actually collected from there. Okay, so but if you have a molecules, like if you have nanoparticles, you have polymer, if you have some molecules, they are not dissolved. If they are not dissolved in organic solvent, then you cannot use ESI, because for ESI your sample need to be dissolved with organic solvent or water. Okay, but if your solvent, for example nanoparticle polymer, they are not dissolved with water or organic solvent, and you cannot use ESI for that type of uh, uh, um, analyte or that type of sample. We can use matrix assisted laser desorption ionization technique. What does this mean? So you have your analyte. Okay, you have your analyte, and then you actually prepare your analyte with matrix molecule. Okay, in this matrix assisted laser desorption, you need to also use a laser. So usually we use a nitrogen laser. Okay, so the nitrogen laser is kind of UV laser. So you see UV light. Okay, so then this UV light interact with the matrix molecule, because this matrix molecule has a conjugated system. Like it has a benzene, it has a lot of pi electron, and pi electron, they can actually absorb the UV light. So that's why we are using nitrogen laser. So you are using nitrogen laser to excite the matrix molecule, and then when these matrix molecule gets excited, they actually donate the proton to your analyte. Okay, so you have matrix molecule, so you have analyte. Your analyte need to be prepared with matrix molecule, these molecules, and you kind of solidify them, and then you apply this. There is a multi-plate. Okay, so and there is a well, small well in the plate, and you deposit your sample with matrix molecule, and then this plate, you have different well number, and then you shine the laser on the well spot, and then the matrix molecule will absorb the UV light, and then it will transfer its proton from them to the analyte molecules, and then analyte molecules will be getting protonated. But in this case, you are ionizing from solid to gas phase directly. You are not using any solvent or anything. You are using solvent, but you are depositing sample as a solid sample. Okay, in the multi-plate. So that's why it's called matrix assisted, because you are using synapic acid or this benzoic acid as a matrix. You are mixing your analyte with matrix. That's why it's called matrix assisted. And then you are using laser to excite the matrix molecule, and you did laser desorption, and then that way you are ionizing your molecules, and then it goes to the mass analyzer. Okay, as you matrix assisted, as you are also using laser, so laser desorption ionization, and you are ionizing solid sample to gas. That's why you need to apply very high voltage, very high voltage. In ESI, maybe I forget to mention, in ESI we need to apply actually 3 to 6 3 to 6 kilovolt of voltage, but in multi we need to apply actually 20 to 25 kilovolt, okay, means 25,000 volt of energy, okay. So that's why, because you are ionizing from solid to gas. So if I show you the scheme, so you have ion source, so this is the ion source, multi source, and this is the multi plate, okay, where you applied your analyte with matrix molecule, okay, matrix molecule, and you apply your sample. So this is different well in the well plate, okay, and then you put the well plate here, and this is your nitrogen laser, which actually shine the 337 nanometer light, and then it's actually interact with your matrix, and it generate the ions, and then you collect all the ions, and this is your time of flight, okay, time of flight tube, okay, and then ions started running through the tube, and then it can reach to the linear detector, and then it can measure the mass. So small molecules will be running faster, heavier molecules will be running slower. So from their velocity and kinetic energy, you can measure the mass. You can use your detector linearly, but you can also use reflector detector, okay? Reflector detector means you will be creating, because if you are generating positive charge, and if you apply positive charge here, then this positive charge that coming from your source, they will be repelling each other, and that way you can redirect them, reflect them to another detector, okay. So we do these things because then we can get high resolution mass spectrum, because if you use linear detector, it's very direct. It will not give you enough time to separate the ions. So as you cannot separate them well, you will get low resolution mass spectrum. But if you use reflector, if you introduce more pathways, more distance, then you can separate them well, and you can have you can improve the resolution, okay. So then this reflector detector actually improve the resolution. So these are the question, question about multi. Okay, so then what is the difference between multi and ESI? Because these are the two important technique. So electrospray ionization, you prepare your sample with organic solvent, and you apply 2 to 6 kilovolt of energy, and you generated lot of charge state, because you are generating ion from liquid to gas. But matrix assisted laser desorption ionization, you are generating ions from the solid, and you need to apply very high voltage, because you are generating ion from the solid, and you may only see one or two class charge state. In ESI, you will see multiple charge state. In multi, you will see only singlet and doublet only. So multi is very harsh, because you are applying very high voltage, and ESI is very soft, because you are applying very low voltage. And then you have another technique that's called direct analysis in real time. Okay, you do not want to prepare any sample, okay, directly. If you have an infected, fungal infected leaf, you want to measure what present in the infected leaf, and you just directly want to analyze without any sample preparation. So how you can do that? So in this case, you need to this is the direct analysis in real time. In this case, you can use some gas. So you ionize the gas. You can use nitrogen gas. You can use helium gas. Okay. So usually, mostly we use helium. So you introduce helium there, and then you apply very high voltage, and then you create metastable helium. okay, and hot helium. And then you have your sample, you put your sample here. This hot helium, when they interact with your sample, then your sample get ionized, okay. That way if you producing some pharmaceuticals, any drug and medication, if you just hold it close to the dart source, you can see the ions in the mass spec. So you do not need any sample preparation. That's called direct analysis in real time, DART. Okay. Then another technique is called desorption electrospray ionization. So usually Graham Cooks, I usually call him my grandfather, although we do not look like same. So he's kind of my grandfather supervisor, because Mark Bear, um, maybe I didn't tell, yeah, I tell you briefly. I'll be talking about Mark Bear. So Mark Bear is my supervisor in the Carnegie Mellon University. Mark Bear, he did his PhD with Graham Cooks. So that's why I call him, grandfather supervisor. So what he did, so if you have a blood sample, if you have a tissue sample, so cancer tissue sample or blood sample, you cannot dissolve your blood sample in the organic solvent, and you cannot perform electrospray ionization, okay, because you have tons of things. You can collect the blood spot in glass slide, and then what he did, instead of dissolving blood sample, he put the sample in a glass slide, and then he actually sprayed ionized solvent. So if you have methanol, ethanol, you electrospray the solvent on the blood sample or tissue sample, then you can do imaging. Okay, I mean if you have a tissue sample, okay, and you want to see what are the metabolites generated in the cancer tissue, then you can imaging. Imaging means you can spot your electrospray solvent on a special part, like specific part of the sample. That way you can identify what are the ion present in that part of the tissue sample, and you do experiment throughout the tissue, not only one spot of the tissue. Because in other analysis, if you have a protein, we collect all the protein and we ran them all at once. But for cancer or injury, this type of sample, you need to know what's happened on the each and every part of the sample. So you kind of do mass spec imaging. Okay, so you hit and then you collect mass spectrum from cancer and non-cancer part, or maybe the cancer is not spread throughout the tissue. Okay, so you need to see how large is the tissue is affected by the cancer. Okay, so that you can do imaging. So if you want to do some kind of imaging with mass spec, so you need to use this uh, desi desi source. Desorption electrospray means you are dissolving all the molecules, not absorbing means you are adding, dissolving means you are removing all the molecules using electrospray ionization. So that's why it's called desi. He's supposed to get Nobel Prize. Currently a lot of my students actually doing his PhD with him. Okay, so then you have different type of mass analyzer. So this is Mark Baer. This is my supervisor. I work with him at Carnegie Mellon University. He is the inventor of this quadruple ion trap mass spectrometer. Okay, so he and his friend John, both of them, when they graduated from Graham Cook's lab, so they started working a small company called Finnegan. You can see Finnegan Corporation. So it's a very small company, and then they invented this ion trap quadruple mass spectrometer. And then Thermo Scientific is a very big company. They actually acquired the Finnegan. They purchased some share of the Finnegan. Then it became Thermo Finnegan, and then eventually Thermo purchased all the share, and then it became Thermo Scientific. but thermoscientific never actually invented this ion trap spectrometer. They have the patent, still they get the royalty. So then my supervisor Mark Baer, he started working with thermo for a couple of years, and then eventually he moved to Carnegie Mellon, where he is still teaching there. So quadruple, quad means four, four means rod, okay? So you have four rod, okay? So this quadruple can act as a mass filter and mass analyzer. So you generated ions, and there are four rod there, okay? Because once you've generated your ions from the ion source, then you need to actually take these ions to the detector, okay? So these are the detectors. So some people ask me at the very beginning that where is the fragmentation happen, where is the trap. So this is the ion, you have ion source here, and this is the sample cone, then you have ion transfer tube, then you have lot of quadruple, lot of rods, okay? That's actually create a road or train so that ion can move through, so if you want to go from Dhaka to Rangpur, you need to follow the train, or you need to follow the road, okay? That can take you from Dhaka to Rangpur. Same thing, if the ions, if you want to transfer these ions from the source to the detector, then they also need a highway or train so that ion can move through the train, because if you do not have any pathways, then it will be lost, okay? So that's why sometimes it's also called ionic train. So how we make this train, okay? Because these are ions, okay? So how we use rods. We use rods, and then we use two voltage. We use two current actually. We use DC voltage and RF voltage. So we use RF means radio frequency and DC. So radio frequency alternate. DC is direct current. Okay. So let's say you have positive ions you created from your ion source. Okay. So then this is the rod that can be in the quadruple or any of these tuple or any hexapole in this ionic train. So then what we do, if it's positively charged, so we put negative voltage. So when positive charge see negative voltage, it goes towards the negative voltage, okay? But when we do not want to lose this ion, because if you have negative charge there, then they will be colliding and they will disappear. Okay, they will be kind of neutralize itself. So when this positive ion goes near to the electrode, then we turn the negative voltage to positive voltage, so that positive is repel, and then so that it can only stay in the lane, it's a specific lane, so that it can go and reach to the detector. Okay, so that's what we do. So alternate the voltage. Okay, so negative to make it forward, and positive to stay in the core. So that's it should not heat. But if we do not like this ion, then we can actually keep the voltage negative. So that way we can use this quadruple as a mass filter. So and then you have a trap. Okay, so you have a trap, so where we can trap the ion. So we use voltage gradient or voltage potential to trap the ions. And then we have conversion dynode. Okay, conversion dynode act as a detector. Okay, so this conversion dynode, um, so when these conversion dynode are made with of copper plate, okay, or the plate that has, that's where electron are loosely bound. Okay, when these ions actually hit the dynode, then this dynode release electrons. So if more and more ions are hitting the dynode, then it will be releasing more and more electron, and then it will create a cascade of electron, and then we count all those electrons to convert these to abundance. Okay, so ions hit to the detector or dynode, and we get, if more ions hitting means it will generate more electron, and it means that this ions abundance is high. If only few ions hit the dynode, it will generate less electron, and then we know that that's ions abundance is very less. Okay, so choosing RF and DC ratio quadruple can act as a mass filter and mass analyzer. So as I mentioned that ion trap, how ion are trapped. Okay, so you can actually trap ions at your home as well. So you need three detector. Okay, so three electrode. Okay, so if you have a these two electrode. Okay, these are kind of half circle shape, and then if you have another detector which is kind of round and circular shape, and then if you apply RF voltage to the middle detector and DC voltage to the end point detector, and then if you actually throw some cornstarch, you can trap the cornstarch actually there, because then it's actually create a trap for ions, because the cornstarch will be ionized, and that way actually you can create a trap. Okay, um, but the physics is very difficult. I know that maybe not too many physics students are here, mostly maybe chemist and biologist or other discipline. So this is the circular electrode at the middle, and then this is two entrance and exit electrode. Okay, so these are two exit and entrance electrode. So um, how ions are trapped actually? How ions are trapped? So it's actually follow hyperbolic field. Okay, so these hyperbolic fields can be solved by Matthew equation. Okay, so this Matthew equation gives us lot of parameter. Okay, so these are the AX and QX. These are trapping parameter. I know that this is when you see equation, it's actually sometimes blow your mind. So this is little bit of electricity and magnetism. So V is the RF voltage, because we also apply RF voltage in the middle electron, and U is the DC voltage. So how much DC voltage we apply, and we also need to calculate the radius. We need to calculate, because this is the middle electrode. You also, it's a circular, so you can also calculate the radius, distance of quadruple. This radius you can calculate, and angular frequency you can calculate, and E is the charge of the ion, and AX and QX are the trapping parameter, and M is the mass. Okay, so using this equation we can calculate the mass to charge ratio. Okay, if we know how much RF and DC voltage we are applying, then using these two equation we can calculate the mass to charge ratio. Okay, so as I mentioned that, as I mentioned here previously, that's these ions need to go through in the middle path. Okay, so if it's actually hit the, when you are driving and you hit a tree or breeze or something which is close, edges of the road, and then it means you were lost. So um, so these all ions. So if we want that all ions should go to the trap and detector, so they need to visit. They need to be stay in this potential diagram. Okay, that's we calculated by Matthew equation. So this is called stable potential for the ions. If ions stay in this region, they are stable, means they can reach to the detector. But if you actually push the ion to unstable region, means if it's hitting the electrode, that way you can actually create quadruple or make quadruple to act as a mass filter. So this is very complicated physics, but during my PhD I try to understand um, how actually this Matthew equation works. So I started with F equal to ma. So that's from Newton law of motion, like second law of Newton. So I think all of you kind of know F equal to ma is is the acceleration, and then you also need to use little bit of calculus, and that way you can actually, if you do all those things, eventually you will be getting this trapping parameter. So this is step-by-step calculation are available in my PhD thesis. I'm just showing that um, um, how we can solve math equation for quadruple, but I'm not actually teaching you core mass spec here. I just want to use mass spec for application. Okay, so but if anyone is interested to know about math equation, how quadruple work, feel free to reach me, and then I can give you the reference so that you can. Okay, so you see that inside the mass spec you have so many things. So it's actually a box of electronics. Okay, so you have lot of things. Okay, as I previously mentioned that this is commercial machine, but this is not commercial. All the mass spec actually developed through the custom made. Okay, so and then once they prove that it can work, and then you actually invite some company and give your patent to the company, and then company make it optimize and make it and keep everything inside a nice box, and then it's okay. But all the mass spec actually developed in the lab, and you can see that there are a lot of wires and things around. Okay, so now I would like to actually show you how how the LTQ work, because this is I'm personally connected with this machine because this is made by my supervisor. So I would like to show how LTQ work. Okay, and then you can see how the trap and the detector, how ion are transferred, how ions are generated. Because some of you asked me question about that, but I kind of stopped you that time. Otherwise, I could not finish the lecture. Like it takes so much time to. So let's see this one. just I want to show you some important parts. As you can see, that's at the beginning. So it's actually generating the. This is the source. This is the HESI source, heated electrosphere ionization, second generation source. You have one and two second generation source, and it's actually generating ions. Okay, and then you see like once it's generated ions, so these ion droplets they enter to the ion transfer tube, and then this is going through the electrode, different type of electrode that we mentioned. Sometimes we call it ionic train because they are traveling through the train. And then this is Velos, this is LTQ. Velos is a so there is a LTQ XL. This is a Velos. Velos has a two type of trap, so low pressure and high pressure trap. Okay, so this is our ion trap where you trap the ions, and then you introduce the gas, and you break down the um, uh, molecules into fragment ions, and these are the Faraday cup or dynode. Okay, so this is the detector. When ions actually goes there, it then you see the yeah. So you see like low pressure cell and high pressure cell. Okay, so at the beginning you have high pressure cell, and then you have low pressure cell. So this is where they separate um, uh, two ion trap. These are ion trap actually. Okay, and then when from trap it's moved to the um, um, electrode, the detector. So that this is Faraday cup, and then you can see all the abundance. Okay. So then there is another mass spectrometer that's called Orbitrap. Okay, so Orbitrap is you saw the quadruple. This is Orbitrap. So you have electrosphere ionization source, and then you have lenses. Lenses means you have electrode. You also have quadruple here. Okay, so you have quadruple here. Then you have a C trap. Okay, it's a like kind of circular trap. So where you trap, and then this is your orbit trap. Okay, so after trapping, you can send your ions there. So ion will be rotating around the middle electrode. So orbital has three electrode. Okay, so entrance and two end electrode, and in the middle electrode. Okay, so ion will be rotating around the middle electrode, and then when they will rotate, they will have different angular frequency based on their mass. So that's you can use to calculate their mass. Okay, and then you can actually after trapping you can send your ion to the collision cell. One person actually asked where is the collision cell. So usually we have collision cell here. Um, so this is the collision cell, high energy collision cell. So you send your ions there, and then you can introduce gas to break down. So what I did during PhD, I actually make a hole here, and I put my laser, so that I use laser to break down the molecules into protein into fragment. Okay, so this is collision, high energy collision cell. So during my PhD, I modified this cell, and I introduced UV and IR laser. That way, I developed my top-down proteomics method. Okay. So some of the, as I mentioned, that you have C-trap, and then you send all these ion packet around the middle electrode, and you rotate them, and then you actually eventually calculate the angular frequency, and then if you know the constant, then you can easily calculate the mass to charge ratio. Okay. You also have some image current detection technique. So orbiter, it can work as a mass analyzer, and it can also work as a detector at the same time. Okay, similar to NEMS and charge detector. So some detector they can actually work as a, but in orbiter, as orbiters actually work in a very high vacuum. Okay, ultra high vacuum. So UHV means ultra high vacuum means 10 to the power minus 10 torr of pressure. It means you have kind of nothing, no molecules, no air inside the orbiter. So that's why you can actually measure very high resolution. High resolution. You can identify molecule with high resolution, very low mass error, and very high mass accuracy. Only 1 to 3 ppm typical. Okay, so because of because you use ultra high vacuum. Um, okay, these are the tune how to operate orbiter app. So here you can divert the control. This is you can put the machine turn on and standby, and here you can control the series pump, and these are the different instrument status, and their scan range. You can scan the mass of your analyte from 100 or 50 to, it depends on what type of molecules you are analyzing. If you are analyzing very high mass protein, then you can use from 500 to 12,000 mass to charge ratio. uh, Whether you want to do fragmentation. So these are the scan parameter, and this is the HESI means um, electrospray ionization parameter you can control. Here is the spectrum window. You usually see chromatogram, and usually you see chromatogram here. Also you can see mass spectrum, and then this is the instrument status. So this is the chromatogram, and this is the mass spectrum. So at the top, this is chromatogram. If you are using any LC, so you will see nice chromatogram. This is direct infusion, so you still see chromatogram. And this is the mass spectrum, where you see the mass of the molecules. Okay. Um, how how does the real data look like? So this is the chromatogram, as you can see. This is angiotensin, a small peptide. So the theoretical mass of this one is 432.8897. So this is theoretical mass, and then you see the mass spectrum measure 432.899993. And if you do the accuracy, it's actually the mass difference or mass error is only 0.37 ppm. So very very good mass accuracy. Okay, so this is insulin. So you see different charge state of insulin, and if you actually zoom out, you can see all the isotopic distribution of insulin. Okay, um, isotopic distribution means hydrogen 1, hydrogen 2 means deuterium, carbon 12, carbon 13, carbon 14, nitrogen 14, nitrogen 15. So you can see all the isotopic distribution if you use high resolution orbiter machine. So you see, like if you have resolution only 17.5 K, so you see there is, you do not see the isotopic distribution. At 35 resolution, you started seeing some isotopic distribution, but in 70K and 140K, you see that this is, you can separate all the isotopic distribution of cytochrome C protein. So if you have this is antibody IgG1. So this is measured in two ways. One is native. Native condition means native mass spectrometry. So using ammonium acetate buffer, you need to do the buffer exchange, remove all the salt, and then you see that this is very folded, and native IgG antibody. And this one is denatured, means you added some acid and organic solvent. Organic solvent will be kind of unfolded the protein, and you can see that 52 plus charge state means it's very very unfolded. And then you can also do some you select these ions, and then you can also do some fragmentation in the collision cell. HCD means high energy collision dissociation, and you can apply different voltage and break down and see how what things inside the antibody. Okay, so we So if you have small molecule drug metabolites, maybe electron ionization or chemical ionization or atmospheric pressure chemical ionization would be more appropriate. um, ESI and HESI for polar analytes, those are soluble in water and alcohol and acetonitrile. Small molecule peptide protein, you can use ESI. If you have biological sample but you have very tiny bit of sample, then you can use nano ESI. For kinetic mass spectrometry also you can use nano. So, if you have polar and non-polar analytes, especially if you have very non-polar polymer nanoparticle, you can also analyze peptide and protein with multi, but it is not recommended for analytes less than 500 Dalton because laser also produce lot of peaks from the matrix molecules. Okay, and if you do not want to prefer not using any sample preparation technique, you can use direct analysis in real time. You do not need to prepare any sample right way. You can put your infected leaf or pharmaceuticals, but the problem is that this can only measure mass up to 1000 Dalton. And then if you have tissue sample, blood sample that you cannot dissolve in organic solvent, then you need to use desi. So most important thing for ESI sample preparation, that's you need to remove all the other particle present in your sample. So you need to use some kind of filter. So you need to make your sample less concentrated, 10 micromolar or 0.1 to 1 micromolar is better. High concentration sample will clog the system. Okay, and yeah, so and at least you need 100 micrometer of sample. Do not use non-volatile buffer or salt. These are not recommended for ESI. Do not use TFA, it does not work well with ESI. Do not use 100% water in negative molecule art, and at least some organic solvent so that desolvation is faster. Use solvent, the recommended solvent is water, methanol and acetonitrile. Do not use THF or acetone, DMS and hydrocarbon. Use little bit of acid if you are performing your work in positive ion mode, then acid will actually protonated your sample and then you will get actually really good spectrum. If you are using your sample in negative mode, use ammonium acetate or ammonium. So add some base actually, so that you can deprotonated your analyte. Okay, so this is, I know that this is very long lecture, uh, but I will be happy to take some question for this.
Recording stopped.
You know that many people already left, so we have 66 people. Yeah, all slide will be provided, yes.
I just have a question that I am just lost in all the techniques and everything actually. So will that be again discussed or the processes and everything in depth in the upcoming lectures, like the graphs and then?
Ionization source will not be discussed, but how we apply these two for proteomics and peptide and protein spectra, that will be discussed, but I will be actually sharing this slide. And then we have a assignment, and in assignment so in the assignment there will be some question related to this technique, and if you just read and find out all those answer of those questions, then you'll be good. But actually in 3 days it's impossible to teach everything, but these are just overview of all the techniques.
Okay. So may we ask some confusions tomorrow before the session
Sure,
if we have some? Okay.
Even
Okay,
if
so
you
thank you.
have some question, because I think I will not maybe able to do the other part today. But if you have any question that okay, any technique you didn't get it, I can discuss it again. Okay.
The today topic is proteomics. We learned in the about the proteomics, ionization technique. But there are many in the many process. Protein is a very large molecule, so it is possible to use all the technique to ionize the protein. And another
Okay, so proteomics can be done by ESI and multi, but mostly we use ESI. Okay, but to discuss ESI, if I just start discussing ESI, but you will not have a strong foundation. Okay, you will have a building of ESI, but without foundation. So then that's why I started talking about how all the ionization source are invented, starting that you already know how cathode ray was discovered. Is that right? Everyone's supposed to know how cathode ray or how electron was discovered from their high school or from their undergraduate. Is that right?
yes, sir. Yes,
Yes.
sir.
So I started from there. I started from J.J. Thomson, and then I just try to tell a story about how all the masses spectrometry are evolved. Okay, you cannot know everything from this lecture, but you will have a broader view. And then when you will do the assignment, that time you will be actually learning and interacting with all the slides, and there it will help you to broaden your idea about mass spec. And then tomorrow and third day we will be more focusing on proteomics and metabolomics. Yeah. And you need to know the fundamentals. If you do not know the fundamentals, then I cannot teach you proteomics. You will not enjoy it, or you will not get uh, all information. That's how this is happening. Okay.
How does ESI differ from capillaries or electrophoresis? So both of them seem quite a bit similar to me.
Capillary zone electrophoresis. This is also another new technique. I didn't discuss that capillary electrophoresis. So in capillary electrophoresis, you apply voltage on the capillary. Okay.
Yes.
Uh, but in ESI, you also apply voltage uh, on the stainless steel capillary, but it's not. It's long, but it's not actually separating anything in the capillary. It's just introducing sample to the ion source.
Simply.
Any other question?
I have a question.
Yeah, sure.
Well, I feel I am entering a new dimension. I am a little bit confused. How do I apply everything I learned from this class in my next steps?
Okay, today you just receive all those information. Okay, so you cannot digest all the information I told you. Okay.
Yes, sir.
I know that is a lot of information that maybe you guys are not expecting. Okay, so that's why we have 1 month. So you will get all this information. I know that it will be hard for you to digest and metabolize all those information, but you have kind of a broader view. And then when you will do the assignment, that time you need to go over with all the slides, and then you try to solve all the problems that we provided in the assignment. That way you learn over the time. And then after when you are done with your assignment and you are interested to join our group as a researcher, then we will give you maybe a project related to proteomics and metabolomics or lipidomics, and then if you continue doing that research project, then eventually you will be expert. Okay, you cannot be expert on first day. I'm sorry.
Yes, sir.
But it will be slow process. It will be slow process. Okay. Usually, like 3 days is not enough for proteomics training, but people, I don't think that they can spend 1 week even. You know. But you will have all those information with you to just enter. Okay. So proteomics metabolomics is a big building. It has lot of rooms inside. Okay. Previously, you didn't have access to enter to the building. This course will just help you to just enter to the building, and today you are kind of in the lobby. And maybe I talked about you with the first room. You just entered and visited. Okay. And then in these 3 days, I will give you all the information, but I am not expecting that you will retain all the information right away. That will happen over 1 month when you will be doing the assignment. Okay.
Yes, sir.
Does make sense? Or
Yes, sir. Thank
any
you.
other question? Yeah.
স্যার আমার আরেকটা কোশ্চেন আছে। আপনি আমাদেরকে কোর্স শুরুর আগে 17টা পেপার দিয়েছিলেন আর কি পড়ার জন্য। সবগুলো যদিও পড়া হয়নি, শুরুর কয়েকটা আর কি পড়তে গিয়ে মাঝে একটা জায়গায় আটকে গেছে, পরেরটা ওটা বাদ দিয়ে দেখা গেছে পরেরটা এগিয়েছে এরকম।
Okay, so that is just for your reference. Okay. But I can tell you, after you doing this course, then you can read the paper and then you will understand. Okay. But you will not understand everything after 3 days. But you will have some basic terms and basic things, like you will see that okay, ions are trapped and this ionized ESI source was used, and this is the mass analyzer was used, and this is how we analyze the data. So this is first day, and I was not expecting that you guys will be reading all the manuscript, all the article we shared. This is just for your future reference. Okay. After doing this training, then you'll have some capacity. Now you will be maybe you will not, at the beginning you will not understand anything from that article. Okay. You read, you everything will blow on your mind that what mistake I did by registering this course. I don't understand anything what they are talking about. Okay. So if you have this feeling, means good. Okay. And second, after doing this class, like first class, now you get little bit more confused. It's created a lot of chaos in your mind. Okay. That's, oh my god, it's so much things, physics and lot of other stuff that I didn't expect it. So you're kind of shocked. If you are shocked and you have anxiety, it means it's good. If you do not have any shock, means you didn't listen my lecture. Okay. After listening my lecture, if you have shock and have some anxiety, it means something entered to your mind, but you do not know what to do with that. You have some uncertainty in your mind. So that uncertainty created some anxiety. That is good. If you have that anxiety, it means good. It means you entered to something very new. And if you do not have any anxiety, and it means you didn't listen my lecture, or you actually didn't pay any attention. maybe you are just waiting for the slides to get, and you may want to just put in your resume, but you maybe from your inner heart you are not committed to learn something very difficult to learn. So what's happened? There is no course or there is no class in Bangladesh in this level. So that's why you are having all those problems. I may be wrong.
I have a question.
Yeah,
That
sure.
is for analyzing the mass spectrometry chromatogram, we
Yes.
should know we have to know about the theoretical mass. That is from the primary structure, I guess. So if I'm dealing with something that is de novo, it means that was not
Okay. So let's say
counting of the primary
okay,
structure.
yeah, I got your question. Okay, so let's say you have a cancer cell and you want to know what are the new metabolites produced in the cancer cell. Is that right? No
Yes,
one
yes.
detected them before. Okay, then you will be doing you will extract and then you will run through the mass spec. So then you need to do two type of analysis. One is single mass spec, means you are not fragmenting. So and the second experiment you will also be doing fragmentation. Okay, and then you need to collect the all small molecules from PubMed, ChemSpider, okay, database. Okay, whenever people identify the new molecules, they deposit to PubMed, chemical structure, or ChemSpider. Okay, all these are called small molecules database. If your molecules is not present in database, you cannot detect. Okay, you cannot detect. Okay, so there are two types of metabolomics. One is targeted metabolomics, one is called untargeted metabolomics. Targeted metabolomics means, like, let's say you want to do some shopping. Okay, before shopping you make a list. Okay, I will purchase potato, milk, egg, salt. You make a list. Okay, you make a target, and then you went to the shop, and then you are just only purchasing the things in your list. This is called targeted metabolomics. Okay, targeted shopping, same thing. And then there is also called untargeted proteomics, lipidomics, and metabolomics. Let's say you have a new shop in a town, you do not know what type of things, or new mall in the town, you do not know what type of things they sell, and you just want to explore. And then you go there, but without any list. That is called untargeted shopping. We call it untargeted lipidomics, untargeted metabolomics, untargeted. Okay, there is a way to do those untargeted things. I will also discuss targeted and untargeted metabolomics. Okay.
Okay, sir. Thank you.
So how do you even know the information about the sequence of the amino acid in a protein? Do you even add them sequentially or systematically? Like
Yes. That we'll be covering tomorrow, actually. Any other question? So, for analyzing data, we need to know some of the
স্যার আমার একটা জিনিস জানার ছিল।
Okay, so just I'm having a little bit problem with my Chrome. It's asking me to sign in. I don't know why it's asking me to sign in because okay, so I'm just joining this meeting. Just give me a few minutes to join it again. Okay. Hello.
Okay, sir.
Listen. Okay, so now I'm good. Okay, so can you guys see me now?
Yes, sir.
Right.
Okay, so what are the other questions you guys have?
স্যার আমার একটা জিনিস জানার ছিল।
Yeah.
যে স্যার আমাদের যে টোটাল যে লেকচারটা হলো স্যার এখানে যে মূলত আমার একটু জানার জন্য যে এই লেকচারটা আমরা আবার ভিডিও সেশনটা কখন পাবো বা কিভাবে পাবো এক আর হচ্ছে এই যে লেকচারের মাঝামাঝিতে আপনি কিছু কোশ্চেন পর্ব রাখেন তো এখানে কিছু ভাইয়ার আপনি কিছু কোশ্চেন করছিল ব্যাপারটা আরো একটু ক্লিয়ার হওয়ার জন্য এই সেশনটুকু কি স্যার ভিডিওতে রেকর্ডে কি রাখা যায়?
না, ওইটা রেকর্ডে রাখা হয় নাই, জাস্ট শুধুমাত্র আমার লেকচারটা রেকর্ডে আছে আর কি।
যদি রেকর্ডে রাখা হয় জিনিসটা তখন আবার একটু ক্লিয়ার হয়।
তাহলে অনেক বড় রেকর্ড হয়ে যায় অলরেডি, ঠিক আছে? যদি ডিসকাশন করি তাহলে মনে করো যে 2-3 ঘন্টার রেকর্ড হয়ে যায়। স্লাইড আর হলো যে আজকের যে স্লাইড গুলো এবং রেকর্ডিং গুলো তোমাদেরকে এই যে তোমাদের যে টিম যে আছে ওখানে অথবা এটা লিংক প্রোভাইড করা হবে।
স্যার এটা জাস্ট সিম্পল সিলি কোশ্চেন ছিল যে আসলে আমরা যে প্রোটিওমিক্স লিপিডোমিক্স এগুলো বলতেছি আমরা কি কার্বোহাইড্রেট নিয়ে এরকম কোনো ওমিক্স বেস স্টাডি আছে কিনা বা আমি জাস্ট জানতে চাচ্ছিলাম কি
যে কার্বোহাইড্রেট হলো যে আসলে ওই মেটাবলোমিক্স এর মধ্যে পড়ে। মানে
এই ওয়ার্ডটা শুনি নাই কখনো আর কি
ওই কার্বোহাইড্রেট আসলে তো মেটাবলিজম বেশিরভাগই কার্বোহাইড্রেট অ্যামাইনো অ্যাসিড এগুলোর উপর, কিন্তু লিপিডোমিক্সটা আলাদাভাবে, কারণ লিপিড যেহেতু একটু স্পেশাল ক্লাস, লিপিডোমিক্সটাও আসলে মেটাবলোমিক্স এর মধ্যে পড়ে, কিন্তু স্পেসিফিকভাবে লিপিড যেহেতু একটা ডিফারেন্ট ক্লাস, সো সামটাইমস লিপিডোমিক্সও বলে।
স্যার আমরা যখন মাস স্পেকট্রোমেট্রি অ্যানালাইসিস করব সেটা তো কোয়ালিটেটিভ অ্যানালাইসিসের মধ্যে পড়ে যাচ্ছে, মানে ক্যারেক্টারাইজেশন মধ্যে পড়ে যাচ্ছে। তা আমি যদি এটাকে কোয়ান্টিটিভ অ্যানালাইসিস করতে যাই তাহলে আমার কি তাহলে নন কোনো কিছুর সাথে কম্পেয়ার করা উচিত? অর্থাৎ আমি যে এলসি করি এলসিতে তো আমরা একটা স্ট্যান্ডার্ড রুল দেই।
So that's why I told you that there are two type of, if you do targeted, okay, তুমি যদি টার্গেটেড করো মানে হলো যে লেটস সে যে তুমি এই আছে বা ব্রেনে তৈরি হয় সেটা যদি তুমি ইয়ে করতে চাও তাহলে ওটার প্রথমে তোমাকে স্ট্যান্ডার্ড কিনতে হবে বা স্ট্যান্ডার্ড তোমাকে কালেক্ট করতে হবে। ওকে, যদি স্ট্যান্ডার্ড তুমি না পাও তাহলে তুমি টার্গেটেড অ্যানালাইসিস করতে পারবে না। এখন তুমি স্ট্যান্ডার্ড পাওয়ার পরে তুমি ইয়ে করলাম, ধরো যে ক্যালিব্রেশন কার্ভ বানাইলা ডিফারেন্ট কনসেন্ট্রেশনে দিয়ে তুমি অ্যাবান্ডেন্স মেজার করলা এলসিএমএস করে, ঠিক আছে? তো তারপরে তুমি ব্রেন স্যাম্পল নিলা, নেওয়ার পরে ব্রেন স্যাম্পলে দেখলা যে কি পরিমাণ ওটা আছে, ঠিক আছে? এই ধরনের একটা স্টাডি, এটা এই রিলেটেড না কিন্তু এই ধরনের একটা স্টাডি আমরা রিসেন্টলি করছি। সেটা হলো যে যদি আমি পেপারটা দেখাই তাহলে আর একটু ক্লিয়ার হবে তোমাদের। সো জর্জিয়া মানে আমি যে স্টেটে থাকি ইউএসএ, তারা হলো অনেক পিনাট তৈরি করে আর কি, ঠিক আছে? তারা হলো যে এগ্রিকালচারে তারা অনেক পিনাট পিনাট প্রডিউস করে আর কি। তো পিনাটের সমস্যা হলো যে পিনাট যদি তুমি রেখে দাও, মানে যখন তুমি সিডিং করতেছো, তো তখন হলো যে ফাঙ্গাল ইনফেকশন হয় পিনাটে। তো যখন ফাঙ্গাল ইনফেকশন হয় পিনাটে, যেমন মনে করো যে এই পিনাটে দেখো যে ফাঙ্গাল ইনফেকশন হয়েছে, রাইট? তো ফাঙ্গাল ইনফেকশন হলে সে একটা টক্সিন তৈরি করে পিনাটের মধ্যে, সেটাকে আলফা টক্সিন বলে। So alpha toxin. Alpha toxin, there are many different type of toxin হয় কিন্তু most deadly হলো alpha toxin B1। এই টক্সিনটা তৈরি হলে এটা অনেক ধরনের সমস্যা তৈরি করে। এখন আমার এক কলিগ, সে হলো যে কি বলে যে গ্রিন গ্রিন ফার্মিং ইন্টারেস্টেড, ওকে, or green pesticides অথবা ফাঙ্গিসাইড তৈরি করতে চায় আর কি, ঠিক আছে? সো মোস্টলি কি করা হয় যে এই ফাঙ্গাল ইনফেকশন যাতে না হয় এ কারণে ফাঙ্গিসাইড, কেমিক্যাল ফাঙ্গিসাইড ব্যবহার করা হয় যাতে এই ফাঙ্গাস এফেক্ট করতে না পারে। তো বাট আমার কলিগ হলো ইন্টারেস্টেড হলো যে ক্লোভ অয়েল মানে লবঙ্গ মানে ক্লোভ, এর অয়েলটা, সে যেহেতু ইন্ডিয়ান মানে ইন্ডিয়ান অরিজিন, যদিও সে ইন্ডিয়া বর্ন করে নাই, সাউথ আফ্রিকাতে বর্ন করছে, ওখানে রেজ এন্ড ব্রট আপ, তারপর ইউএসএ তে আসছে। তো ক্লোভ অয়েল সে ব্যবহার করতে চায় এবং ব্যবহার করে সে এই ফাঙ্গাল ইনফেকশনটা রিডিউস করতে চায়। এই ফাঙ্গাল ইনফেকশনটা রিডিউস হয়েছে কি হয় নাই সেটা আমরা বুঝবো যে যদি সে কি পরিমাণ আলফা টক্সিন তৈরি করছে। তো আমরা প্রথমে যেটা এই স্টাডি যেটা করছি সেটা আমরা কি করছি, এই আলফা টক্সিনটা আমরা কিনছি, ঠিক আছে? কেনার পরে আমরা এলসিএমএস করছি, মানে এই আলফা টক্সিনের আমরা মানে কোন 5 ppm 1000 ppm 15 ডিফারেন্ট ppm এ আমরা আলফা টক্সিন এলসিএমএস করে আমি তাহলে অ্যাবান্ডেন্স পাইছি, পাওয়ার পরে আমরা একটা স্ট্যান্ডার্ড কার্ভ তৈরি করছি, ঠিক আছে? দিস ইজ আলফা টক্সিন কনসেন্ট্রেশন, this is the abundance, then we get the y equal to mx plus, and then we also identify the limit of detection and limit of quantification from our machine, okay? এরপরে আমরা হলো যে ও এই ফাঙ্গাস গ্রো করছে আর কি, ঠিক আছে? নিজেরা গ্রো করছে, গ্রো করার পরে সেই ফাঙ্গাল একটাতে হলো যে কোনো এই এই পিনাটের মধ্যে, এই ছবিটা যদি দেখো তাহলে এই পিনাটের মধ্যে কোনো ক্লোভ অয়েল দেওয়া হয় নাই, 0 ppm মানে কোনো ক্লোভ অয়েল আমরা দেই নাই। আর অন্যগুলোর মধ্যে আমরা 200 ppm 2000 মানে 1000 ডিফারেন্ট অ্যামাউন্টে ক্লোভ অয়েল দিছি, ওকে? তো দেওয়ার পরে আমরা কি করছি যে এটাকে আমরা পেস্ট করছি, করে কি পরিমাণ আলফা টক্সিন তৈরি হয়েছে সেটা আমরা কোয়ান্টিফাই করছি আর কি। এবং আমরা দেখছি যে যখন আমরা কোনো ক্লোভ অয়েল ব্যবহার করি নাই তখন আমরা আলফা টক্সিন পাইছি খুব বেশি, ওকে? সেটা ইন্টেন্সিটি ছিল খুব বেশি, অ্যাবান্ডেন্স ছিল খুব বেশি। এবং যখন আমরা 500 ppm ক্লোভ অয়েল অ্যাড করছি তখন দেখো আলফা টক্সিনের পরিমাণ কমে গেছে। এবং স্লোলি আলফা টক্সিন আমরা যখন 2000 ppm ব্যবহার করছি আলফা টক্সিন আসলে প্রডিউসই হয় না। ফুল ওয়ার্কটা এলসিএমএস দিয়ে করা হয়েছে।
আরেকটা কেস আমি আপনার সাথে অ্যাড করি, সেটা হচ্ছে যে অনেকগুলো পেপার আমি পড়েছি যেটা অ্যান্টিবায়োটিক রেসিডিউ টেস্ট করা হয়েছে এলসিএমএস এ পোল্ট্রি মিটে। এখানে আপনি যে কেসটা বলছেন আলফা টক্সিন প্রডিউসড হয় বাই ফাঙ্গাস এন্ড সেটার একটা স্ট্যান্ডার্ড নিয়ে কিনে ওটার এগেইনস্টে দেখা হয়েছে যে অ্যাসোসিয়েশন কেমন,
মানে প্রোবায়োটা কি
প্রোবায়োর সাথে
Yes.
প্রোবায়োর সাথে অ্যাসোসিয়েশন কেমন। কিন্তু যখন অ্যান্টিবায়োটিক চেক করা হয় পোল্ট্রি মিটে, কারণ পোল্ট্রিটাকে যখন ফিড করা হয় অ্যান্টিবায়োটিক অ্যাজ এ প্রিবায়োটিক বা অন্য কোনো পারপাসে, সেটা এক্সাক্ট অ্যান্টিবায়োটিক হিসেবে থাকে না। ফর এক্সাম্পল কিন্তু মেটাবোলাইট হয়ে যাচ্ছে। তো আমি দিচ্ছি স্ট্যান্ডার্ড হিসেবে দিচ্ছি আমি সিপ্রোফ্লোক্সাসিন, বাট আমি রেসিপিতে চেক করতেছি সিপ্রোফ্লোক্সাসিনের মেটাবোলাইট। তাহলে স্যার আসলে আমার কাছে এই জায়গাটাতে আমি একটু কনফিউজ,
এখানে
হাউ মেটাবোলাইট we can estimate against formula calibration curve using main standard as a ciprofloxacin.
এখন যদি তুমি এক হলো যে তুমি যদি কোনো এক হলো যে তুমি আনটার্গেটেড করতে পারো। ওকে, এলসিএমএস এর একটা সুবিধা হলো যে তুমি আনটার্গেটেড, তুমি হয়তো অনেক ধরনের অ্যান্টিবায়োটিক অ্যাপ্লাই করছো এবং এটার বডিতে গেছে যে হয়তো এটা মেটাবোলাইজ হয়ে গেছে এবং ওখানে ডিপোজিট হয়েছে, তাই না? ডিফারেন্ট এজ লেভেলে ডিফারেন্ট ভাবে ডিপোজিট হইতে পারে। বাচ্চাদের জন্য একরকম হতে পারে, বড় মুরগির জন্য একরকম হইতে পারে, ঠিক আছে? তাহলে এখানে তাহলে তোমাকে করতে হবে আনটার্গেটেড মেটাবোলমিক্স। ওকে, আনটার্গেটেড মানে হলো যে তুমি নেওয়ার পরে এখানে স্মল মলিকুল কি আছে, তো সেটা আমরা হলো যে সেটার জন্য দুইটা সফটওয়্যার লাগবে। যদি তুমি আনটার্গেটেড প্রোটিওমিক্স করতে চাও সেটার জন্য প্রোটিওম একটা সফটওয়্যার ডাউনলোড করতে হবে। আর যদি তুমি আনটার্গেটেড মেটাবোলমিক্স বা মিক্স করতে চাও সেটা হলো কম্পাউন্ড ডিসকভারি একটা সফটওয়্যার আছে, যেটা আসলে একটু পরেই দেখানোর কথা আর কি আমার। তো সেখানে আমরা যেটা করবো সেটা হলো যে ওই সফটওয়্যারের মধ্যে মিস্টেড, তারপরে পাবমেড, কেমিক্যাল স্ট্রাকচার, সব ওয়ার্ল্ডের যত স্মল মলিকুল আছে সেটা আছে ওখানে,
ডাটাবেস আছে।
ইয়েস, ডাটাবেস লিংক করা আছে সফটওয়্যারে। এখন তোমার মাসপেক যখন তুমি রান করবে তখন তো তোমার পিক থাকবে, এবং তুমি যদি ফ্র্যাগমেন্ট করো এমএসএমএস করো তাহলে সেটাও থাকবে। তাহলে সেটা যখন তুমি ওই ডাটাবেসের এগেইনস্টে সার্চ করবা তাহলে সে তোমাকে কম্পাউন্ডের লিস্ট দিবে।
That means without using any standard, we can analyze
quantify. You cannot quantify, but you can do you can do identify. You can identify.
presence of absence.
But if you want to do quantify, you can quantify. Then you need some kind of standard or isotope labeling. Okay. Then you need to do some control study. But then, okay. So when we will talk about lipid like metabolomics, we will talk about that. That will be third day discussion.
Thank you, sir. ছোট্ট একটা সাজেশন দরকার ছিল, একটু কথা বলতে স্যার। আমি একটু কাজ করেছিলাম যে তুলসী এন্ডোফাইট থেকে তাদের অ্যান্টিমাইক্রোবিয়াল প্রপার্টি গুলো আইসোলেট করছি, তারপর আমি এক্সপিএলসি করে আমার টার্গেটেড কম্পাউন্ডটা পিউরিফাই করেছি। আমি তারপর যখন এন্ডোফাইটটা ডাব্লিউজিএস করে কিছু টুলের মাধ্যমে আমি জানতে পারলাম, মানে প্রেডিক্ট করতেছি যে আমার অ্যান্টিমাইক্রোবিয়াল কম্পাউন্ডটা হচ্ছে কি মেবি নোবেল। তো স্যার এই মুহূর্তে আমার পিউরিফাইড কম্পাউন্ডটা নিয়ে মানে আমি এলসিএমএস যদি করতে চাই, আমি কি এলসিএমএস করে এটার ওয়েটটা জানতে পারবো অথবা কি স্টেপ নেওয়া যেতে পারে এই মুহূর্তে স্যার পিউরিফাইড কম্পাউন্ড?
স্যার এইটা তো হলো যে ইন্ডিভিজুয়াল প্রবলেম, সেটা আমরা ওই সফটওয়্যার গুলো মানে আমি দেখাই দিই যে তোমরা কোথায় থেকে সফটওয়্যার গুলো ডাউনলোড করবা, করার পরে আমি যারা মনে করো ঘুমাইতে চায় তারা চলে গেল, তাহলে আমি মানে সেশনটা শেষ করে দেই। তারপরে যারা তাদের পার্সোনাল কোশ্চেন আছে তারা থাকলো, এরকম করলে কি বেটার হয় একটু নাকি?
একটু বেটার হয় স্যার, কারণ হচ্ছে অনেকে কালকে ক্লাস লেকচার এক্সামস আছে।
আমি জাস্ট আমাদের যে লাস্ট লেকচার যেটা আছে সেটা আমি একটু শেষ করে দেই, দেওয়ার পরে তারপরে বলি যে যাদের পার্সোনাল বা বিভিন্ন ধরনের কোশ্চেন আছে তারা থাকতে পারে। ওকে, তো সবাই এই লিংকে যাই আর কি, এই লিংকটাতে যাই যেখানে আমরা যে, আচ্ছা এটা আমি রেকর্ড করি তাহলে সুবিধা হবে আর কি।
স্যার এটা রেকর্ডেড থাকলেই ভালো হবে।
Yeah, yeah.
Recording in progress.
So can you see the actually the thermoscientific?
Yes, sir.
First, okay. So you if it I so you need to register. Okay, I already registered. So if you click here, please register if you do not already have access to the demonstration software. Okay, so if I just right click here, then you can see this. So you do not need to register as a purchase software. You need to register as a demo software. Okay, you can register as a purchase software, then you need to pay. Okay, you need to pay like maybe $10,000-$20,000. I don't think that you intend to purchase. Okay, so then you go there. Can you see what I'm showing?
Yes, sir. You can see.
Okay. So you just need to, it's kind of, simple registration. You need to write down your name, email, and country. Okay, and then you just need to say yes. That way you actually register the demo software. Okay, not the purchase. If you click on purchase, then that's has less information, but that will not give you the access. So demo software. Okay, so you register this. Once you register this and get your login information, for example, my login information is my email and I have password, and then I can log in. Okay, and then we already purchased instrument in our university, but I'm actually showing you the demo software. So if you log in, you can see that there is a demo software. Okay, so then if you go to the demo software, so from here you need to you need to download couple of software. Okay, the first one is called application freestyle. Okay, so if you click, so you need to download freestyle software. Okay, tomorrow we have lecture on freestyle software, so that you make sure that you download your freestyle software. You can download any of the version. Okay, so you can download the version from 2023 or 2021. I would suggest that you download the latest one.
So are they compatible with Linux?
Maybe not. So if you go there, it's mostly these are all Windows software. Okay, may not be applicable to. Okay, so you need to as I mentioned, that's freestyle. So we'll be using this freestyle software. Okay, and then for two other things. Okay, so you can also install another software that's called Excalibur. Okay, Excalibur or Excalibur. Okay, freestyle you download. You need to download Excalibur. Okay, you can download the latest one. But this Excalibur is you can only use for 2-3 months. Okay, it's not free. The freestyle one is free. Okay, Excalibur is not free. You can only download the trial version. And then
স্যার এগুলো ক্র্যাক ভার্সন পাওয়া যায় না,
sorry,
ফাইল করে যে পেয়ে সফটওয়্যারগুলো ইউজ করা হয় এটা আর কি পাওয়া যাবে?
Yeah, so that means you need to buy the instrument, okay? Then you can purchase those, okay? So those are expensive, okay? And then you need to download two other software, okay? Very important. One is Proteome Discover, that what we'll be using for proteomics, data analysis, and then Compound Discover that we'll be using for metabolomics, lipidomics, or any small molecules, okay? So that we'll be mostly using in third day. Tomorrow we'll be using freestyle and Excalibur, but especially we'll be using freestyle. So you make sure that you downloaded these 4 software. How many software you need to download? 4. Okay, so one is freestyle, Excalibur, Proteome Discover, and Compound Discover. Okay. But then if you have problem with downloading this software, okay, if your computer having some problem, then you might need to also download thermoscientific foundation software, okay? This may be thermoscientific foundation software. So 90% all of your actually other releases. Yeah. So if you go to other release, in any case, okay, so in any case that your freestyle or Excalibur or Proteome Discover or Compound Discover software is having problem and showing some error, or if it shows that you need to actually download foundation, thermo foundation, which is free software, then you need to download the foundation 3.1 or like SP11 or 10, okay? Any of these foundation software, okay? That will solve the problem. Okay, so then this is done for today's lecture. So, but if you have any specific question or your personal project question, you can stay. Other people can leave and we can see you guys tomorrow at the same time. Okay?
আপনি আজকে যে লেকচারটা পুরো শুরু থেকে দিলেন সব বলা যায় বেশিরভাগ জিনিসই বুঝিনি, কিন্তু মানে হালকা হালকা আইডিয়া পেয়েছি বা এরকম যেটা হয়েছে। এখন এটা কালকের ক্লাসের জন্য আমার কতটুকু জানা দরকার, আপনি যখন স্লাইড দিবেন সেটা কি পড়লেই হবে আজকের মধ্যে?
না না না, টুমোরোস লেকচার হলো যে আমরা ওকে আমরা ইনস্ট্রুমেন্টেশন কিভাবে কাজ করি সেটা শিখলাম। টুমোরোস লেকচার হবে হলো যে আমরা কিভাবে ডাটা অ্যানালাইসিস করব, প্রোটিন বা পেপটাইডের কিভাবে ডাটা অ্যানালাইসিস করব সেটা শিখবো। সেটার জন্য এটা জরুরি না জানা, কিন্তু যখন তুমি ওই যে কি বলে অ্যাসাইনমেন্ট করবা তখন এই টেকনিক গুলো সম্পর্কে জানতে হবে আর কি। ওই অ্যাসাইনমেন্ট যদি তুমি সাবমিট করো তাহলে তুমি অটোমেটিক্যালি ওগুলো জেনে যাবে আর কি।
আচ্ছা স্যার, থ্যাংক ইউ স্যার।
স্যার আমার অপারেটিং সিস্টেম হিসেবে আমি উবুন্টু ইউজ করে থাকি, তো এখন আমার লিনাক্সের জন্য আমার কি করা লাগবে বা আমি কি করতে পারি?
লিনাক্সের জন্য হয়তো বা তোমাকে ওই যে লিনাক্সের মধ্যে যেহেতু উইন্ডোজ একটা মেশিন ব্যবহার করা যায়
জি স্যার, ওয়াইন।
সো সেটা হয়তো ডাউনলোড করে তুমি উবুন্টুর মধ্যেই উইন্ডোজ ব্যবহার করতে পারো।
আচ্ছা স্যার, ট্রাই করে দেখি স্যার।
এই সফটওয়্যারের কোনো লিনাক্স ভার্সন নাই।
অল্টারনেটিভ যেগুলো আছে লিনাক্সের ওইটা কি কাজ করার মতো হবে স্যার? আমার কোনো আইডিয়া আছে স্যার?
আমি আসলে ডিটেলস জানি না, কারণ যেহেতু মানে আমরা যখন মেশিন কিনছি বা ইয়ে কিনছি সবগুলো উইন্ডোজে, তবে আমি ওটা এক্সপ্লোর করি নাই আর কি।
আচ্ছা স্যার, ধন্যবাদ স্যার।
একটু আগে যে কোশ্চেন করতেছিল যে তার একটা পার্সোনাল প্রজেক্ট ও কি আছে না চলে গেছে?
জি স্যার, আছে স্যার।
ওকে, এখন বলো তোমার প্রজেক্টটা একটু লাউডলি বলো, তখন আমি আসলে ভালোভাবে শুনতে পারি নাই।
স্যার আমার প্রজেক্টটা ছিল স্যার এন্ডোফাইটিক ব্যাকটেরিয়া নিয়ে। তো আমি তুলসী থেকে এন্ডোফাইটিক ব্যাকটেরিয়া আইসোলেট করে তাদের অ্যান্টিমাইক্রোবিয়াল কম্পাউন্ড সেপারেট করছি। তো তারপর সেই মিক্সচার থেকে আমি আমার টার্গেটেড কম্পাউন্ডটা এক্সপিএলসি করে পিউরিফাই করেছি। তো এখন স্যার এই পিউরিফাইড কম্পাউন্ড হচ্ছে এটা অ্যান্টিমাইক্রোবিয়াল অ্যাক্টিভিটি আছে। তো আমি ওই এন্ডোফাইটটার আবার ডব্লিউজিএস অ্যানালাইসিস করে দেখলাম যে আমার মানে বিভিন্ন টুল আছে অ্যান্টি স্ম্যাশ বাগেল ফোর, ওইখানে আমি অ্যানালাইসিস করে দেখলাম যে আমার টার্গেটেড কম্পাউন্ডটা মেবি নোবেল আর কি, কিছু অ্যামিনো অ্যাসিডের চেঞ্জ আছে। তো এখন আমি এটাকে যদি মাস্ক করতে দেই, আমার কাছে যে পিউরিফাইড কম্পাউন্ডটা আছে, তো এটা আমি কিভাবে মানে কোন মাস্ক এলসিএমএস দিব, তাহলে ওরা আমার কাছে একটা মলিকুলার ওয়েট জানতে যাচ্ছে আমার কম্পাউন্ডে, কিন্তু আমি তো এটা মলিকুলার ওয়েট জানি না। তো সেক্ষেত্রে আমি কি বলবো? আর
থাকে তাহলে তুমি কি দেশে না কোথায় কাজ করো?
জি স্যার, আমি দেশি।
ওকে, তাহলে তোমাকে হয়তো বিসিএসআই এর তাদের এলসিএমএস আছে বা মাস স্পেক আছে। তো
তাদের সাথে যোগাযোগ করছি, তাদের মেশিনটা এই মুহূর্তে আর কি অ্যাভেলেবেল না, মানে কাজ করতেছে না গত 3 মাস যাবত আর কি স্যার।
এক্সপেক্টেড তুমি কি রকম মোলার মাস এক্সপেক্ট করতেছো? এটা কি স্মল মলিকুল না বিগ মলিকুল?
জি স্যার, এটা একটা ছোট্ট পেপটাইড আর কি, এটা মোস্টলি 27 to 31 অ্যামিনো অ্যাসিড।
ওকে ওকে, সো তাহলে ওই এলসিএমএস করতে হবে। ওখানে যে ওই শাইনুজ্জামান আছে বিসিএসআই এর, আমি জানি না তার সাথে তুমি কথা বলছো কিনা।
স্যার ওদের মেশিনে নষ্ট, আমি জানি।
ওকে, তাহলে যদি ওনার মেশিনটা ইয়ে থাকে, তাহলে যদি তোমার ওই যে যে মেজারমেন্ট একটা ইনস্টিটিউট আছে না, বাংলাদেশ মেজারমেন্ট সায়েন্স, ওই যে ইয়েস, না না, ওই যে মালা খান আগে ইয়ে ছিল আর কি। উনি তো এখন মনে হয় নাই। ওই যে বাংলাদেশ মেজারমেন্ট ইনস্টিটিউট, ওকে, বিআরআইসিএম, ইয়েস ইয়েস, ওদের ইয়ে আছে, ওদের মাসপেক আছে। ওদের হলো যে ওখানে যদি রাজু আছে, তো আমার একটা স্টুডেন্ট ওখানে আবার কাজ করতো, মিরাজ মিনহাস, আমি জানি না, ও মনে হয় ও হলো ইন্টার্ন হিসেবে কাজ করতো। আচ্ছা দাঁড়াও, আমি রাজুর হয়তো বা একদিন আগে আমাকে, নাম হলো মাহমুদুল হাসান রাজু। তো ওর সাথে মাহমুদুল হাসান রাজু, তো ওর সাথে যোগাযোগ করতে পারো, ঠিক আছে? তো ওদের ওখানে এলসিএমএস আছে। তাহলে ওখান থেকে তুমি মাস পাবা। আর যদি তুমি মনে করো যে এই বাইরে তুমি স্যাম্পলটা পাঠাইতে পারবা, যদি পিউরিফাই থাকে, যদি মনে করো যে আমার এখানে পাঠাইতে চাও, তাহলে আমি এখানে মাস মেজার করে দেখতে পারি, এবং এনএমআর নিতে পারি। পেপটাইড তো এনএমআর ডিফিকাল্ট, মাস মেজার করতে পারি এখানে। ওখানে যদি না হয় তাহলে এখানে পাঠাই দিতে হবে। তাহলে তুমি কোথায় জব করো? আমার ওই যে প্রফেসরের সাথে কাজ করো, মানে এটা ওই স্যাম্পলটা যে আমাকে পাঠাইতে হবে সেটা একটা অফিসিয়ালি পাঠাইতে হবে, এরকম না যে র্যান্ডমলি তুমি স্যাম্পল পাঠাইলে। আবার দেখতে হবে যে স্যাম্পলের মানে ঢাকা ইউনিভার্সিটি, ওখানে লিখে পাঠাইতে হবে যে রিসার্চ রিলেটেড প্রফেসর টু প্রফেসর, মানে এরকম যদি হয় তাহলে সমস্যা করবে না। মানে র্যান্ডম স্যাম্পল আবার ইউএসএ তে কাস্টমে আটকাই দিবে।
আপনার এই কোর্সটা করার পেছনে আমার অনেকদিন ইচ্ছা ছিল, যেটা আমি একটা ফার্মা কোম্পানিতে জব করি। তো স্বাভাবিক ফার্মা কোম্পানিতে স্যার দু একটা ইনসেপ্টার ছাড়া স্যার এলসি এপিআই এবং ইনসেপ্টার ভ্যাকসিন ছাড়া এলসি এমএসএমএস নাই। তো এলসি এমএসএমএস সম্বন্ধে আমি অনেক ঘাটাঘাটি করে দেখলাম যে স্যার এটা নর্মাল এলসির মতো না, ডাটা অ্যানালাইসিসটা এটা সবচেয়ে ডাটা অ্যানালাইসিস এবং এক্সপ্লেনেশনটা সবচেয়ে টাফ আমার কাছে মনে হয়েছে। তো আপনার
আমরা
আজকে
আলোচনা করবো আর কি।
জি স্যার জি স্যার আজকে
Yeah.
জি স্যার আজকে আমি মাস অ্যানালাইজার যখন আপনি ডিসকাস করছেন, টাইম অফ ফ্লাইটটা একটা ইজি লাগছে আমার কাছে। আমি অরবিট ট্র্যাপটা নিয়ে আমি আসলে জানতে চাচ্ছিলাম, কারণ আমি সাইএক্স এর ওদের যে বাংলাদেশে ইয়ে আছে, মেশিন আছে 4500, ওইটার সম্বন্ধে আমার একটু ধারণা নিয়েছিলাম আর কি। আমি মাঝখানে বেলবাড়িতে কয়েকদিন গিয়েছিলাম, ওদের আছে এখন অবশ্য আউট অফ অর্ডার। তো ওইখানে ওদেরও অরবিট ট্র্যাপ আছে আর কি। ওইটা স্যার ওই মাসেল এই জিনিসটা আমি স্যার ভালোভাবে বুঝি নাই আর কি, যদি একটু আরেকটু 1-2 মিনিটে ব্রিফ দিতেন জাস্ট ইয়েটাতে।
শিওর, আমি ওই স্লাইডটাই ওপেন করতেছি যাতে আপনার ওকে। সো মাস অ্যানালাইজার কোয়াড্রুপল অনেক ডিফিকাল্ট টু আন্ডারস্ট্যান্ড অ্যাকচুয়ালি। সো